All right, so today we're going to review what exponential growth and decay graphs look like. And so in order to do that, we need to remind ourselves of what an exponential function looks like. Expo functions are the ones that look like a times b to the x power, where a and b are coefficients, numbers of some sort, and x is the variable. The b value is the number that's actually going to control whether or not we have growth or decay. Depending on what number b is, we either have a growth factor or decay factor. So if b is growth, then it's going to be greater than 1. And if b is decay, then that value will be less than 1. Simultaneously, it has to also be bigger than 0. The decay factor and growth factor will never be negative and will also never be 1. The a value then is our starting amount or the initial amount, which we see on our graph as our y-intercept, unless there's something extra added at the end of the equation. So, for example, let's start by looking at an exponential decay graph. The basic form of it would be y equals, and we just pick some number as our starting amount. How about 4 times 1/2 to the x power, right? Notice 1/2 is less than 1. So to graph this function, we go to our handy dandy calculator and just type it in. 4 times 1/2, didn't hit the divide by button, 1/2 raised to the x. And then just select our standard window zoom 6, which will graph from -10 to 10 in the domain and in the range. And you notice from left to right, the function is going down. It is decreasing. If we trace certain values on this graph, like at 0, notice the y-coordinate is 4. That was our initial amount from our equation, 4. If I allow x to be 1, right, just one whole number later, 1/2 to the 1 is 1/2, times 4 is 2. So we're getting exponential decay by 1/2. Let x be 2, y is 1. Let x be 4, y is 0.5. And the function will continue to decrease forever and ever and ever towards the x-axis, never actually touching it. So to see an example of exponential growth, we just need to think of an equation that will have a b value greater than 1. And there's a whole lot of numbers you can think of there, that being 4 times 2 to the x value. So back to our handy dandy calculator, and we type in the function 4 times 2 raised to the x and graph that. And now we see from left to right, the values for y are increasing or growing. If we trace specific values like 0, you see the starting amount is still 4, just like it was before, except the values will now double. So if we trace 1, 2 to the first is 2 times 4 gives me 8. If I trace 2, it's doubled again. 8 times 2 is 16, right? So it's just going to be an additional factor of 2 every time. And of course, these values have gotten so high that they don't reach, they're above the top of the graph. Notice the y values are all above the graph, above the x-axis, because they can never be 0 with exponential growth or decay, unless we were subtracting some value at the end. So now you see the example of exponential growth, where the graph increases from left to right, and the example of exponential decay, where the function decreases from left to right, both of which are controlled by this growth or decay factor b, depending on the value of b. The starting amount is the a value, the number in the front, in which case both functions has a value of 4.